Green's functions as solutions, mostly to boundary value problems, although you can solve them on unbounded domains too. Let's go through an example of that now. So let's say we have the following just ordinary differential equation that is just a bounded solution that has a bounded solution at positive and negative infinity. And we just want to find the Green's function for this operator here, okay, which is defined on the real line. Q is just going to be some constant greater than 0. And then we're going to have the additional conditions on the limits that u needs to go to 0 as x goes to positive and negative infinity. Okay, so this is constructing the Green's function. Of course, it's different than solving the ODE itself. And the important thing to remember is that typically for a Green's function, you want it to be able to be acted on by the operator and result in a delta distribution. So you will always have piecewise smoothness essentially at the origin in this case, and you exploit that in order to get your delta function out of the operator acting on G. Okay, so so just a reminder, right, is that our Green's function is going to be continuous, right? But typically you expect to find a kink in it, and essentially it solves the problem, okay, with a unit delta source at a point, okay? And so the solution in this case is to note that, well, for this ordinary differential equation, right, the associated ordinary differential equation for G is going to be, well, it's going to be a partial differential equation in x and y, because we need something that we can integrate against an inhomogeneity. Okay, so G of xy here is going to solve the following PDE. Okay, essentially it just needs to be acted on by this differential operator and produce a delta distribution. Okay, and in this case, x and y are both going to be real numbers, and we also need for G to inherit the boundary conditions. Okay, so it needs to tend to 0 as x goes to infinity. Okay, so how do we handle this problem? Okay, well, if you notice, right, this problem pretty much is just a homogeneous problem everywhere but a single point. So the approach is to solve it like a homogeneous problem everywhere but a single point. And then across that single point, you need to be able to integrate this and get something that has measure 1. Okay, so those are the three things you do. You solve it to the right of the singularity, you solve it to the left of the singularity, and then you say, when I integrate the differential operator acting on G across the singularity, I should get 1. Okay, and that should constrain everything along with your boundary conditions. Okay, so let's see what this looks like. So we're going to start by defining, okay, just a change of variables, z equals x minus y. Okay, So in this case, the differential operator is still going to look the same, okay? But now we're going to rid ourselves really of any involvement of sort of multiple variables, okay? And furthermore, right, so the limit as z goes to plus minus infinity is going to be g of z plus y equals 0, okay? For any y that lives in R. Okay. So essentially what we do is we're going to solve this independent of y and then shift it, okay? So because the differential operator only involves z, right? And because essentially this boundary condition, right, it doesn't really matter what y is as long as it's, finite. It's the same as saying, the limit is g of z for any value of y goes to 0 as z goes to infinity. Okay. So we're going to basically break our domain in 2, okay? And we're going to have z is less than 0 and z is greater than 0, okay? So let's start with z is less than 0, okay? At this point, we're only going to have one of these boundary conditions, right? The z goes to minus infinity one. That's where we need boundedness on this side. So what we have then is minus g z plus q squared g. And this is the advantage of bounding ourselves away from 0 is that delta distribution is just 0 there, okay? Well, this is should be not hard to solve, right? Our general solution here in this case, right, it's just a linear second order differential equation. It's going to have the form a minus e to the qz plus b minus e to the minus qz, okay? And we can rid ourselves of one of these pieces, right, from the boundary condition. Which of those goes away? We need boundedness as z goes to negative
exponential.
Yeah, right. So we need to rid ourselves of the negative exponential because remember, it's q is greater than 0, okay? So basically, as z goes to minus infinity, we want g to go to 0. So this implies that b minus is equal to 0, okay? So we have about half of our solution, but we're still going to have to do a little bit of work on the around the z equals 0 point. Okay. All right. So that's the first half. Can I turn the page? Okay. Z equals 0, or sorry, z greater than 0 looks quite similar. So we have minus gzz plus q squared g equals 0. I have then a g of z. A little bit of an abuse of notation. I'm just writing g as a function of z here. We'll write it out fully as a function of z and y momentarily. Okay. Has the same form, right? But remember that as z goes to infinity, okay, we need for g to go to 0, okay? And so that means that this solution is problematic. So a plus needs to equal 0, okay? So we have a piecewise defined solution, okay? A minus e to the qz for z less than 0, and b plus e minus qz z greater than 0, okay? Now, we want g to be continuous, okay? And we also need this sort of jump condition on the boundary too. And so that will restrict our remaining 2 coefficients, right? Continuity, what does that say? Well, it says that I need at z equals 0, I need a minus and b plus to be equal to each other. Okay, so continuity requires essentially that a minus equals b plus. So I need to have g be a continuous function. Okay, c0. So those are the same constant, and we then get that this g of z is equal to e to the minus q absolute value of z. Okay. Yeah. Okay. All right. So what's the last part? The last part now is having our singularity have the right mass. So that's a condition essentially on the integral. So what do I mean? Specifically, the integral of the differential operator acting on g, right? This should equal the delta distribution. So if I integrate it over just a really small window right around 0, that should be 1, no matter how small I shrink epsilon, as long as epsilon's positive. So remember, this is equal to the integral between minus epsilon and epsilon, right? And this is equal to 1, okay? And so if I recall that g is going to be continuous, right? If I shrink epsilon small, right? We're just going to have that this condition implies that g sub z, okay, evaluated at z equals 0 is equal to -1 in this case. Okay, so what does that imply? Okay, that implies that minus qa minus qa is equal to -1. Okay, this implies that a is equal to 1 over 2q. So sorry, this here is our, this is not evaluating this here. This is like the jump. Okay. So I mean, what is essentially the jump in g sub z, okay, from just less than z equals 0 to just slightly more than z equals 0. Okay. So you could also write it as, you know, the limit of g sub z as epsilon goes to 0 from above minus the limit of g sub z as epsilon goes to 0 from below. All right, so that's why you get these two terms here. Okay, so this should be equal to -1. So that means a is equal to 1 over 2q. So g of z is equal to e to the minus q absolute value of z divided by 2q. Okay, so this implies that g xy then is equal to e to the minus q over x minus y divided by 2q, right? Because remember, way back at the beginning, we made this change of variables with z. Now we have a function of just x and y. Now, this is our Green's function, right? That's what we wanted. You could check this, right? You could, you know, plug it back into the boundary value problem that we wrote down for the Green's function and check that everything works out. Okay. The last thing I'll write is what is the general solution to the inhomogeneous problem. Okay. Well, remember, right, u of x, right, is just going to be the integral over our domain of g of x, y, f of y, dy, okay, which in this case is going to be e to the minus q x minus y, okay. f of y over 2q integrated with respect to y in that case. Okay, so essentially it's just this convolution of this absolute exponential, this sort of decaying exponential function. And so the way that the differential operator essentially spreads out the discontinuity is through this sort of exponential smoothing process. Okay.
Can you say again why? So I get that we require its integration over the discontinuity to be, or over the cusp to be 1. So why does the jump then have to be -1 in the derivative?
Just because there's a minus sign here. So I just moved the minus sign over to the other side.
Okay. And we know it shows up just in the first derivative.
Because this integral here, right? This integral is 1, right?
Right.
Yeah, so if you, I'm going to write that on the next slide here. So yeah, I mean, I can unpack this a bit better, right? So if we do this, right? So yeah, if you're okay with that, the G part's going to go away because it's continuous, right? This part is not continuous, right? We know that this needs to equal 1.
I followed. That was the part that was screwing me up, was G went away, so we were just dealing with GZZ integrated.
Yeah, so sorry. Yeah, I was a little fast and loose with this, but yeah, essentially we have this minus this is equal to 1. But then yeah, you can flip the sign here. Okay.
Totally. Okay.
And then this is the thing that we call the jump, right?
Right.
This jump term at z equals 0. Yeah.
Okay. Thank you.
Yeah, no problem. Okay. So yeah, the approach for these kind of problems, and I mean, I think, you know, maybe a problem or two on the homework is similar to this, right? But maybe in higher dimensions, I think, for one of them. Yeah, so you should be able to get all these homogeneous solutions sort of surrounding your singularity, okay? And then to deal with your singularity, you just have to write down an integral condition, right? The only way to really make sense of the delta distribution is to integrate it, right? And you could integrate that against a test function. You could just integrate that against a constant, and we'll just get back 1, and that'll give you the full restrictions that you need on your coefficients. Any other questions about this? All right, cool. So yeah, I mean, I thought that might be helpful. It seems relevant to the homework problem. Okay, so yeah, we're actually pretty good on lecture.